Alright, we've gone through the exact approach using the force method, or also known as the flexibility method, also known as the method of consistent deformations, to find this middle support reaction of 444.79. Right? And just through simple equilibrium, then sum of moments at one point gives us the reaction at the far right, vice versa. Sum of moments at the right will help us to get the other one. Now in this case, because of the static indeterminacy we have no choice but to have to use intermediate results to get the other results. So if there's an error in this 444.79, these other two are also going to end up being in error, even if they could be in some version of equilibrium with each other. That all get revealed in the shear moment diagram as we work that out. So let's see how that all gets played out here. We follow up with the reaction at the left. We follow then with a slope according to the load downwards. At every meter there's a drop of 20 kilonewtons, down, 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 all the way over to 240.6. And we note here by similar triangles that going from the shear at the left to zero shear is 7.97 meters. And then likewise, if we go another 7.97 meters, we'll end up with the mirror reflection that we've got of that shear. That's going to be a useful thing for us on the moment diagram. But we're going all the way down over here to that middle support. The reaction jumps us up to 204.2, and then again as we head down because of the uniform load, then we end up with a minus 95.8 at the end, and we end up closing off. And again, note all these various distances that we get by similar triangles that identify critical features or locations of critical features in the moment diagram, which we have this gull wing shape, right? Second order, because if we take a derivative of a second order, we get a function that is a first order, right? Parabola becomes in the derivative a straight line, and that's what we've got here, right? Those are the relationships that we have going on between shear and moment. And then that change of moments given to us by this area, right? So 7.97 times the 159.38 divided by 2 is this 635, turns out to be almost exact 635. And then we drop down, and this whole area here takes us to the minus 812.5. Now note, please, that we went up to 635 over 7.97 feet, and so that means that we'll come down to 0 over that exact same 7.97 not feet, but rather meters distance. Now I didn't draw it particularly well because I was a little sloppy in pulling out my French curve when I drew this by hand, but that's okay, right? All we have to do is get it kind of reasonably close in that kind of qualitative way, and that we get our distances. I was a little sloppy here, 7.97. I didn't really feel like rewriting that, so I called it about 8, and that's also to connect up with some other things that are going to be discussed here in just a little bit. Right? And same thing coming from the right, and we come from the right to the left to that middle support, we end up with a minus 812.5 from either direction. Remember, from our estimate, that was where we had a discontinuity in our guess about where the inflection points were located, right? And so back then we had guessed the 20% rule, so that put, for those outer spans, and that put the inflection point at 4 meters from the middle support. Well, it was almost exactly 4, so that was pretty good. Now on the right side, though, we said 20%, that would have been 3 meters, but we didn't end up there. We ended up 5.4 meters, so that's 0.36 of L over here on this right side for that location of the zero moment, or the inflection point in the deflected shape. And so that was why we had an error in what turned out to be mostly an error over what was going on in the right-hand span. We actually guessed really well in the left-hand span, not so much in the right-hand span in terms of where that zero moment was located. Right? So you can go, this time you could actually walk your way all the way left to right, do all the numbers, and you would close off to 0 the way you could, or what we were doing at that beginning thing was to go from the outsides and work our way to the middle, see if we met where we were supposed to be. Right? So let's talk a little bit about some of the lessons we learned in all of this, and part of that is when you have a two-span and the spans are asymmetric and with the uniform load, the inflection points move away from the middle support. And what you'll find, the general rule of thumb actually is about 1/10 of the span for the middle spans. But when you get to those outer spans, it increases away from the support because of that flexibility that is showing up out here at those pin supports. Right, and we'll talk about that more in just a second. Right, but the inflection points move away from the 1/10 rule into something that is more in the range of 0.2 to 0.3. We had 0.2 on one side and 0.36 on the other. So this is just some sort of rough guide. It's not some absolute that you're going to be working with. Right? Now the other thing that's going to happen is that the shorter span, we should observe, turns out to be stiffer of the two. Now stiffer in what kind of sense here is important, but it's not too hard to imagine. Again, with this longer span here and these loads pushing down, causing the beam to bend, you're going to get, with that longer span, a bigger displacement, right, compared to over here in the shorter one. And then the consequence is going to be that this beam in the middle is not going to have zero slope. Unfortunately, I kind of drew it that way. Instead, it's going to have a counterclockwise kind of rotation to it to help accommodate what it wants to do, which is it wants to deflect more in that longer span. So in the next part, we're going to take a look at the computer modeling and try to understand that in some sort of greater detail.